Good morning, guys. Hope you're doing well. So we'll continue our introduction of complex numbers. Now, you know that real numbers, integers or real numbers, can be plotted on a Cartesian plane. And just a reminder, the Cartesian plane is the XY plane. You guys probably hear that word so often, the Cartesian plane. That's the XY plane. I think it's named after this guy, Descartes. Not how you say the name. I think it said Descartes, something like that. Funny French people. Anyways, the Cartesian plane is the XY plane, the normal XY plane on which we can graph all real numbers, basically. That's the Cartesian plane. But we need to have a way to also be able to graph complex numbers, imaginary and real numbers. We need to have a way to graph complex numbers such that we can perform all normal operations that can be performed on real numbers. So on this Cartesian plane, the x-axis is called the real axis because that's why you plot the real numbers. Just think of it as your number line where you can put the real numbers, and the y-axis is the imaginary axis where you plot the imaginary numbers. So this axis will have numbers like 1i, 2i, 3i, 4i, just in increments of I. So a small example here is if we want to graph 2 plus 3i, negative 2 plus 3i, I'll go to the real axis, look for negative 2, then I'll go to the imaginary axis, look for 3, and then I know that my complex number is right there. So that's my complex number, 2 plus 3i. So you can draw your complex numbers and they'll end up looking like that, or whichever the case. And just using a binoculars to look into the future, I hope there's some properties about this you can see. You can see that there's an angle there which can be found. You can see that the size of this complex number is something that can also be found because I see an element of Pythagoras and a triangle. So it's just a peek into what could come in the future. So another here, if I want to graph this complex number, on the real axis it's 3, and on the imaginary axis it's negative 4. So that's here. Then I'll draw my complex number like that with an arrow at the end. So first calibrate this again. So yeah, I can graph my complex number, and just remember to make it have an arrow at the end to indicate the direction of the complex number. We can evaluate complex functions just like we can evaluate real functions or normal functions. This is a complex function that is, this is a function that's 2x squared minus 3x, and I can, if my input is a complex number, my input is a complex number 2i, then I can evaluate that complex function by substituting for that input. So in place of x, I'll put 2i squared minus 3 into 2i. Now, this is 2, open brackets, 2i squared is the same thing as 2 squared I squared, minus 3 times 2i is, I hope you can see, is 6i. So really, these numbers are following the same operation, same treatment as real numbers. The only thing we need to note and look out for is that I is the square root of negative 1. So I have 2 squared is times 4, 2 squared is 4, 4 times 2 is 8. I have I squared here, I squared is the same as negative 1, so that means I'll multiply that by negative 1 minus 6i, and my answer ends up being negative 8 minus 6i. Same substitution is happening here for people who like to see it better like this. So 2i is going in there twice, which is 4i squared, which is 8i squared minus 6i. Put in the negative 1 for I squared, and you end up with negative 8 minus 6i. Another example is here. I need to substitute for 3 plus I in place of x. So that will be 3i squared minus 5 into 3 plus I plus 2. So to solve this, like I said, treat them the same way you treat real numbers, real expressions. I hope you remember that the expansion of a plus b squared is a squared plus b, a squared plus 2ab plus b squared. Or if you want, you can go the long way, say a plus b into a plus b, and then you FOIL. This goes with this, this goes with that. You FOIL this, and then you end up getting the same thing if you expand it. So I'm just going to use this because I can. So that's what I'm going to use. It's going to be 3 squared plus 2 times 3 times I plus I squared. Now subtract 5 times, negative 5 times 3 is negative 15, and negative 5 times I is negative 5I plus 2. So down here I have 9 plus 2 times 3 times I is 6I. I squared, I hope you remember, is negative 1. I have negative 15 minus 5I plus 2. So the only thing I have to do now is collect like terms. I'm going to collect the like terms, the real terms of this equation, which is 9 minus 1 minus 15 plus 2, and the imaginary parts of this equation, which are 6i. I'm just trying to put them apart. 6i minus 5i. I think those are ones. Then I end up with 9 minus 1 is 8 plus 2 is 10 minus 15 is negative 5 plus I. So same treatment as real numbers or as normal numbers, because they should follow the same. They should follow the same rules. They should obey the same rules of mathematics. So yeah, this is again the same thing worked out professionally. Substitution, simplifying, collecting like terms, and then you end up with same thing. Now there's something called a complex conjugate. In mathematics, a conjugate is a number, can be a number. In this case, a complex conjugate is going to be a number that is the opposite of the complex number. And a complex conjugate is formed by changing the sign, to change the sign of the imaginary part of the complex number. So the complex conjugate of a plus bi will be a minus bi, because we'll have changed the sign of the imaginary part of the complex number. When you add a complex number to its conjugate, or when you multiply a complex number by its conjugate, the result is supposed to be a real number. So one way you can make a complex number real is just add its conjugate or multiply by its conjugate. Now, what are some applications of this idea? First of all, practice with conjugates. If I want to find the conjugate of this, it's simply 2 minus I root 5, because I only need to change the imaginary part of that complex number. What are some applications? Again, this one, so you can think of this as 0 plus negative half of I, where 0 is the real part. And if you want to find the conjugate, you simply change the sign of the imaginary part, so it will become positive half I. So basically that conjugate is half of I. This is one application of this complex conjugate. And before I go there, I want to remind you of something that you used to call rationalization of the denominator. I hope you remember this from 8th grade. Rationalize the denominator. And sometimes you just sing it and not even know what it meant. But just to remind you, if you have a number like 1 out of the square root of 2, this number, this is supposed to be a fraction, but we have a non-rational number, or we have an irrational number in the denominator. An irrational number is a number that cannot be expressed as a fraction. So if you have an irrational number in the denominator, then if this is your solution is not very aesthetic, or it's not very, it doesn't look complete if you still have a non-simplified term in the denominator. So one process that can help to get rid of that is if I multiply by the same thing, up and down, because initially it was 1 over root 2, but if I multiply by the same thing up and down, it looks like as if I've not changed the meaning of the expression. But that's going to help me, because in the numerator 1 times root 2 is root 2, and in the denominator root 2 times root 2 is 2, because it's root 2 squared, which is 2. So I have been able to remove the irrational number from the denominator. I have made an irrational number to become rational. So that's the process of rationalizing the denominator, so that your solution can look complete or simplified or better. So that's the same principle we're following here. Now we have a complex number that has an imaginary part, or that has a complex part in the denominator. And by the way, I hope you remember that if this was, say, 2 minus root 2 over 3, what is this? Minus root 2 divided by 3 plus root 5, then you could still rationalize by multiplying this by its conjugate, which the conjugate was 3 minus root 5, or is 3 minus root 5, 3 minus root 5. Because when you, in the denominator now, it looks like a difference of squares. This is review of 8th grade. If you're getting lost here, just, go get some water and come back in 30 seconds. If you simplify the numerator, because in the numerator you're going to do the FOIL and then be able to simplify it, but the denominator, since it's a difference of 2 squares, hope you remember that a minus b into a plus b is equal x squared minus b squared. The denominator is simply going to become 3 squared minus square root of 5 squared, and we both know, we all know that square root of 5 squared is just going to be 5. So in the denominator you'll just have 9 minus 5, which will have simplified dramatically. So that's the same idea we're applying here, that we're trying to get rid of the imaginary part from the denominator and make it a real part. Make sure the denominator ends up with a real part. And since in radicals we call it rationalization, don't you guys think we should call this one realization? This is the part where you laugh. Anyways, if we want to realize this denominator, we're going to multiply this whole expression by the conjugate of the denominator. So we're going to multiply both the numerator and the denominator by the conjugate of the denominator. This is helpful because it does not change the meaning or the outcome of the whole expression, because mathematically this cancels with that and you end up with the same thing. So it doesn't change the outcome, but it helps us to make the denominator a real number. So in the numerator I have 2 plus 5i, and in the denominator I have 4 times 4 plus i. In the denominator I have 4 minus I multiplied by 4 plus I. Now sidebar here is again reminding you of a difference of squares. A squared minus b squared is the same thing as a minus b into a plus b. So that means that if I see this somewhere, I can summarize it into this, right? So fortunately for me, I see that difference. I see that multiplication of conjugates in the denominator, so I know it's going to be summarized by this difference of squares up here. So let me first work with the numerator. I'm going to FOIL, so that will multiply that. 2 times 4 is 8. 2 times I is 2i. 5i times 4 is 20i. And 5i times I is 5i squared. In the denominator, I have a difference of squares, so it's just going to be 4 squared minus I squared, right? 4 squared minus I squared. I'm simply using this definition up here that if you have two factors that are the same except for the sign in the middle, which is the opposite, then I know that that is the expansion of this difference of squares. So I'm going to go ahead and simplify. In the numerator, I have 8 plus 2i plus 20i plus, now I know that I squared is the same as negative 1. Negative 1 times 5 is negative 5. And in the denominator, again, I squared is negative 1. So this is basically 4 squared minus negative 1. So simplifying numerator, 8 and 5, 8 minus 5 gives me 3. 2i plus 20i gives me 22i. 4 squared is 16 minus negative 1. So I end up with 3 plus 22i divided by 15. I have written this complex number without an imaginary part in the denominator. I've made the denominator a real part. So I'll ask you again, do you think this should be called the realization of a complex number? I make a strong case, because if you made it rational, it was rationalization, so shouldn't this be realization? Anyways, let's try some more practice. I want to perform the indicated operation and express the result as a simplified complex number. Now going back here, a simplified complex number should not have an imaginary part in the denominator. That's why we went ahead to realize it. For this one, I have two. The only part that I see that's difficult or contentious is that negative square root of 12. Now, I know that square root of 12 is the same as square root of negative 1 times 12, all divided by 2. I also know that that can be broken into square root of negative 1 times square root of 12 divided by 2. I can simplify that because I know that the square root of negative 1 is I. So I have 2 plus I root 12 divided by 2. Now, that is simplified because I don't have the negative square root anymore, but it's not in its simplest terms because 12 can still be broken down. So that's 2 plus I square root of 12, which is the same as 4 times 3, divided by 2. 2 plus I square root of 4 times square root of 3 divided by 2. 2 plus I square root of 4 is 2, so that is 2 times I, which is 2I times square root of 3 divided by 2. Now I'm at a point where I can divide, or to be safe, to do this very safely so that I don't confuse you, I can factor out 2, 1 plus I root 3 divided by 2, and then at this stage I can cancel out the 2's and end up with 1 plus I root 3 as my simplified complex number. Do you have to go through all the steps I went through to do this? No. You can just move from here to this step, or from there directly to this step, and then from this step directly to that step. So you don't have to do everything the way I did it, but I'm just trying to show you where everything goes. Again, performing the indicated operations and simplifying the complex number. This one, negative 2, I'm just simplifying and collecting like terms. Negative 2 minus 4i plus 1. 1 times positive 1 times, positive 1 times 1 is positive. Positive and a positive is still a positive. I'm doing that because if this was a negative, some people could have just written this out instead of bringing this in to each of the terms. So that's just something you should know. Alright, simplifying this, collect like terms. This is the real part, this is the real part. Negative 2 plus 1 is negative 1. This is an imaginary part, this is an imaginary part. Negative 4i plus 6i is 2i. My complex number is simplified. Example, I was talking about 2 minus 3i. When this negative goes here, it makes the 3 negative. The negative goes there, it makes the 2 negative. So real number, all this is real number. So 2 minus 3 is negative 1. Complex number, imaginary number, negative 3 minus 2 is negative 5i. Or the step that I missed here is just to write 2 minus 3 minus 3i minus 2i, which eventually came to that. Multiplication, you can use FOIL, you can use expansion. I'm going to use FOIL. The 2 goes to the 4, that is 8. The 2 goes to the negative I, that's negative 2i. The 3 goes to the 4, that's 12i. The 3 again goes to the negative I, that's negative 3i squared. So collect like terms, or before we go there, let's simplify the I squared. 2i, 12i, 3i squared is the same as 3 times I squared, but I squared is negative 1. So that's 3 times negative 1, which is negative 3. So collecting like terms, this is a real number. This is also a real number. That's 8 plus 3. This is an imaginary number, and so is this one. So that's negative 2i plus 12, which gives me 8 plus 3 is 11. Negative 2i plus 12i, is 10i. So this one, it is also a complex number that has, it's a complex fraction. It's a number that has an imaginary number in the denominator, and the first thing I need to do is make sure that that denominator does not end up with an imaginary number. I can do that by multiplying the numerator and denominator by the conjugate of the denominator. The conjugate of the denominator is negative 2i. Hope you can see that. Conjugate of the denominator is negative 2i. Now, interestingly enough, if this I is a power, is an odd power. No, let me not go there. Conjugate is negative 2i, negative 2i. Maybe what I can ask you to do is check, because you might be wondering, do I always have to multiply with the negative power? So check. If I have 1 out of 2i, and I multiply with a positive 2i and a positive 2i, does that get rid of the denominator of the imaginary number in the denominator? Part 2. If I just multiply by I and I, does that get rid of the imaginary number in the denominator? Part 3. If I have 1 out of 2i squared and I multiply with I squared and I squared, does that get rid of the imaginary number? Part 4. Same thing. This time multiply with, by negative 2i squared and negative 2i squared. Does that get rid of the denominator? So these are some simple experiments you can do for yourself just to get a better understanding of how this getting rid of the denominator works. Okay, so what I need you to figure out from this is, do you have, if it is only the imaginary part and it doesn't have a real part in the denominator, do you have to make it negative? Do you have to multiply by the exact conjugate, or can you do it without using the conjugate? That's what you should ask yourself. So for this question, in the numerator, I have negative 5 plus 3i being multiplied by negative 2i, or you can put that in front. negative 2i, and in the denominator I have 2i times negative 2i. So in the numerator, negative 2i times 5, that's going to give me 10i, and negative 2i times 3i, that's going to give me negative 6i squared. So 10i minus 6i squared divided by, in the denominator, 2i times 2i is 4i squared, but it's negative. So 10i minus 6i squared in the numerator becomes 10i minus, remember, I squared is negative 1. 6 times negative 1 is negative 6. Negative of negative 6 is positive 6. And negative 4i squared in the denominator, I squared is negative 1. Negative 1 times negative 4 is positive 4, which I can simplify because the numerator has a 2, which I can factor out. 2 into 5i plus 3 divided by 4 by 2 once and by 2 2. So my final answer becomes 5i plus 3 divided by 2. That's my simplified complex number. Alright, you should have encountered this on your extra credit challenge, but a simple way you can always do these numbers is ask yourself what power do I know, and how many times do I need to raise it to get the power that I want. So for I15, I know 15 is the same as 5 times 3, and I already know what I to the third power is, so I just need to raise that to 5 powers. Right? I know I to the power 3 is negative I, and I need to raise it to 5 powers. If I raise negative I to 5 powers, what do I get? This is the same thing as negative 1 power 5 times I to the power 5. So you're going to be discovering ways that you can break this down in the simplest form for you. I'm going to just share one more way that you could do this. So this negative 1 power 5 is still negative 1 because it's an odd power. And I to the power of 5 is basically the same as I to the power of 2. I to the power of 5, I hope you did this on your own, was positive I, because it's I to the power of 4 times I to the power of 1. Hope you'll agree with me that this is negative of I. That's what I end up getting, because I to the power of 4 is 1. Now what I was saying, a way that you can figure this out in different ways is we have a pattern here. I to the power of 1 is I to the power of 2, negative 1, I to the power of 3, negative I to the power of 4, 1, I to the power of 5, I to the power of 6, guess what? Negative 1, I to the power of 7, can you guess it? I to the power of 7, anyone? Negative I to the power of 8. What do you think it's going to be? 1. I to the power of 9. What do you think it's going to be? I. Do you see a pattern? I, negative 1. Negative I, 1. I, negative 1. Negative I, 1. I. So I hope you can see that if you follow this pattern, I of 15 is an odd number, right? So if I manage to find what I of 16 is, because I know 16 is simply the same as I to the power 4 squared. If I have I to the power 4 squared, that gives me 16. And I know I to the power 4 is 1. If I square that, I get 1. So if what I'm getting is 1, then the number before it, so this is where I'm at. If what I'm getting is 1, the number before it was negative I. So I to the power 15, since this is 1, I 16 is 1, the number before it is negative 1. I to the power of 15, because 15 is just before 16, is supposed to be negative I, which is the same answer that we got here. And if you want to prove it, you can go and say, well, I to the power of 16 has given me 1, but I to the power of 15 is just I to the power of 16 divided by I to the power of 1. So I'm just going to get this 1 and I divide it by I. Then if I want to use the process of making it a real denominator, I'll multiply by I, multiply by I, or if you want, multiply by negative I. Then in the numerator, 1 times negative I is negative I. In the denominator, I times negative I is negative I squared. But again, in the denominator, negative I squared is the negative of negative 1. Because I squared is negative 1, which is just positive 1. So you still end up getting negative I. So yeah, I may have said so many things to do something simple, but just trying to show you how you can approach it different ways. Okay, this is going to be your homework. Enjoy.